Okay, from Princeton University, who will talk about insights into the rotating black hole interior from numerical solutions.
Okay, thank you very much. And again, thank you for the organizers for inviting me to this conference in this very interesting city and place. I have to apologize that unlike most of the other talks here, I'm not going to give any theorems. So it's a very different style of approach to understanding something about general physics. So yes, I'm going to talk about insights into rotating black hole interiors from numerical solutions. Here's a rough outline of what I'm going to talk about. So I'll give a little bit of a motivation why I'm interested in studying interiors, and perhaps more from sort of the physics perspective or the astrophysics perspective. And thankfully, sort of Mihalis and Spiros gave a sort of a very nice overview of the expectations and what we currently know about interiors. And so I could have had several slides where I was going to go over kind of the same thing, but luckily I can now very quickly go over that, kind of skip that, and go over some of the later results in a more mannered pace. So I will kind of, the only thing that I'll really say, I'll kind of rehash some of the basic properties that we expect to see in rotating black hole interiors, but kind of focusing on the problems that we're facing in trying to get numerical solutions. So in particular, so I'm not going to give any theorems. So my approach to studying general relativity is through numerical methods, to trying to find numerical solutions to particular situations. So of course, we can't prove anything in general with numerical methods, but what we can do is give sort of case-by-case solutions to some degree of accuracy controllable by the resolution of the simulation, and give them full details of the solution. So what would be nice would be, for example, if to get some insight into what might happen in the interior from a black hole formed from gravitational collapse, is to solve the equations numerically and see what happens. And from those particular case studies, gain insight into what might be generic properties of the interior. And probably like many of you know is that the last few decades there's been a lot of progress in numerical solution of the Einstein equations, and particularly applied to the exteriors of black holes, black hole collisions, etc. They're the kinds of things that LIGO has started to see. And so you might think that, well, okay, now it would be pretty straightforward to take those techniques and apply it to the interior. And unfortunately, that's not been the case. So I'm not going to be able to actually show you nice examples for the situation that we want. We're still in the numerical space, restricted to the so-called the poor persons or the toy models, where we have to essentially use spherical symmetry. Or what I'll show you is results where we can actually get angular momentum in the space-time, but we have to go to 2+1 dimensional asymptotically anti-de Sitter space-time. So that essentially there we have circular symmetry, but in terms of the PDEs that we have to solve, it still just depends on an R and a T coordinate. And that's the only case where we can really get sort of some tractable handle on the numerics. And essentially, I'll explain in a little bit more detail, but the problem is the coordinates, the gauge. Okay, so what is my motivation? Well, I'm kind of I'm interested in classical general relativity. And I think one of the most fascinating solutions in Einstein's theory are black hole solutions. And it's really just to therefore understand all aspects about black holes as predicted by Einstein's theory. Now, because if cosmic censorship is upheld in astrophysical situations, we likely won't see aspects of sort of strong field gravity leading to singularities in any observational context. Arguably, the Big Bang is one example, but the consequences of that were, I guess, so unpalatable to physicists that they invented inflation to hide the Big Bang singularity as predicted by relativity. So it might be that the most extreme regimes of general relativity, even where classical relativity is valid, so the approach to the singularity might be censored. But still, if black holes do exist, sort of by, I think, reasonable extrapolation, some parts of the interiors as predicted by classical relativity should exist. And so we should be able to understand what goes on in the interiors, at least prior to the singularity. And of course, now we've got very good evidence, growing evidence that black holes do exist. Sort of the very nice overview slide that Annegret had in her talk on Monday. I mean, the last 20, 40, 50 years, there's been growing circumstantial evidence that black holes exist. And in fact, one of the best evidence on that front, the orbits of stars around the period of black hole in the center of our galaxy, that was also co-awarded the Nobel Prize with Roger Penrose, so to Gez and Gensel for studying the orbits around an object in the center of our galaxy. Of course, they were in the Nobel Prize, they were careful to not use the word black hole there, because it's not giving evidence for black holes, it's giving evidence for an ultra-compact dark massive object in the center of a galaxy, which is consistent with it being a black hole. And actually, perhaps more exciting in terms of understanding or knowing that black holes, as described by general relativity, exist is the gravitational wave observations of LIGO. So that's about as close as we can get to a direct probing of space-time around black holes. And even though at the moment, the signal-to-noise ratio is not great to make very precise consistency constraints with relativity, so far we can make quantitative constraints and it is consistent with relativity. So black holes, let's just say they do exist out there in the universe and likely as described by relativity. But therefore, that also means that therefore the interiors do exist. There are many billions of black holes out in the universe, at least a few supermassive black holes per galaxy, and many thousands to tens of thousands of solar mass black holes per galaxy. So we know there are many regions in the universe where these things exist. In other words, where gravitational collapse happens. And then we know from relativity that space-time is going to flow to some kind of singularity or some kind of incompleteness, which is actually a pretty profound statement that one of our fundamental theories of nature, there actually are places in the universe where it's evolving to a state where, I guess what exactly happens there is perhaps a matter of philosophy at this stage, but I think most people, including myself, would say that classical relativity is telling us that it's failing to explain what happens as you approach the singularity, and some new theory has to take over. Let's call it quantum gravity. So one reason for studying classical relativity in the approach to the interiors, other than just the intrinsic interest of what's going on, is it might tell us something about how Einstein equations are breaking down and therefore inform some theory of quantum gravity, how to fix the problems of the singularity. Again, there are many approaches. We've already heard from several talks here, Mihalis, Spiros, about sort of the mathematical approaches. I'm going to be focusing again on the numerical approaches where we try to find case-by-case solutions. And there are going to be several other talks at this conference by Maxime and several others that are going to also continue to look at the analytic approaches. Okay, so what is the problem? Why can't I sort of give you an example of the realistic asymptotically flat four-dimensional Kerr black hole interior? And the problem is the gauge. And in particular, the methods that are most well developed right now are sort of the Cauchy type evolution scheme, where it's a Cauchy initial boundary value problem. So we specify some initial data on a Cauchy surface, and then we want to evolve that forwards in time. But of course, in this case, we don't know what's going to happen in the interior in particular. And so in particular, we also don't know what coordinates we need to map out the space-time in a way which is non-singular before we get to the actual singularity in the metric. So we don't want coordinate singularities to form. So in practice, then, what it means is that we simultaneously have to solve the Einstein equations together with a set of equations that tell us what the coordinates are going to be. So we actually have to provide additional, whether they simple algebraic constraints, but more typically there actually are differential equations that we solve for the coordinates as we evolve the space-time. So we simultaneously, have to solve for these things. And at the moment, there's really no sort of dynamical coordinate conditions or coordinate equations that have been proposed that is likely to work in the generic interior. Except in spherical or circular symmetry. And when I show the case with the BTZ case, it's kind of trivial in spherical symmetry how to find these coordinates, but those things are probably going to break down away from spherical symmetry. But this is also, this next point is kind of the same thing. But even if we do find, some dynamical coordinate condition that is non-singular until the actual singularity, whatever form it takes, if it doesn't reach the singularity sort of at the same time, if all our t equals constant slices aren't in sync such that they reach the singularity at some constant time slice, then we're going to have to deal with perhaps a very complicated boundary to our domain. We'd have to do some form of singularity excision, and there's no reason to expect that that's going to be a simple boundary. Again, in spherical symmetry, it turns out that that's a pretty trivial problem to deal with, and you'll see it in the examples that I give with the 2+1 dimensional case. And just to sort of illustrate this more with Penrose diagram, you can sort of perhaps appreciate what the problems might be. And so, again, thanks to Mihalis and Spiros, I can sort of skip some of these stuff and just kind of go to the sort of the punchline. So, okay, here's our kind of best guess, perhaps, for a simplified form for what the interior might look like. So again, this is a Penrose diagram. So, I've just started, this is asymptotically Minkowski, asymptotically flat. I mean, you can cut it off here. We have the star. We could start at some time here. In this diagram, the star is sitting here. It's stable for all time up until some point. Then something happens and it undergoes collapse. It collapses down to a space-like branch to the singularity. A horizon forms. Future time like infinity, future null infinity, space like infinity, past null infinity. And so the now already celebrated the Fermat's space-like singularity conjecture. And I assume that this is the first time I heard about it on Monday, so I assume we can attribute it to you. But this is kind of but this is kind of the sort of in a rough schematic way what we might expect for the interior. So there probably is some form of space-like branch to the singularity at the origin, which is strong in the sense of tidal deformation. So any objects that try to approach this branch will get tidally destroyed. But then, thanks to the proof of de Fermat and Luke, that we know that in general, when there is rotation, that is the generic situation. There has to be some form of rotation in astrophysical black holes. There will be a segment of the Cauchy horizon. This will be a weak singularity probably, and in some sense probably getting stronger and stronger as you approach the space-like branch. And weak in the sense, again, in one way of thinking about it in terms of the tidal strength of the singularity. So objects might actually survive reaching the Cauchy horizon. But okay, then, so based on this, now we want to say, okay, we don't really know what this is. Let's start with the Cauchy slice. And what's the problem? So now, so in the numerical evolution case, okay, we specify data on some Cauchy slice we want to evolve towards this point. And here, I guess that the first sort of problem, which is, okay, this here I'm framing it as a coordinate problem, but it actually is a very physical aspect about what happens with black holes. Is if we know that there's a piece of the Cauchy horizon that we have to get to understand this full structure, this slice has to evolve all the way up until that point, or at least close enough so that we can say that we are sort of asymptotically close to that point. Of course, we'll never get exactly there in some numerical scheme, but sufficiently close. But then that implies that by the time we get there, the entire future evolution of the exterior universe has already happened. Because this is complete. The affine, in terms of affine time, null geodesics here go to infinity, all time-like curves that that stay outside, they live forever. T goes to infinity. So the entire future evolution of the universe happens before this slice can reach there. The other problem then is, as I mentioned before, is so now we also expect that here there might be some space-like branches, but as the slice is evolving, what happens if it runs into a piece of the space-like singularity well before this part? And that we typically expect would happen, and it does happen in the cases that I'll show you. And so, of course, in numerics, whenever a singularity means something is going to go to infinity, something fails to be invertible, etc. Something goes wrong. Computers don't deal with it, they crash. So the first singularity we encounter, whether it's a coordinate singularity or a physical singularity, the code breaks down. So we have to deal with those two situations And again, in spherical symmetry, it's kind of trivial, as but trying to extend it beyond spherical symmetry. There have been some proposals. People have proposed various coordinate but there haven't really been any serious attempts, and at least to my knowledge. And I think part of it is that, okay, most numerical relativists are too excited with the new toy of gravitational wave physics that they're playing with. So they want to do as much with, the kind of thing that LIGO could see as possible. So perhaps when they get bored with that, they'll start going back to some of these interesting open questions in more theoretical relativity. So they're not that many people that are actually trying this, but so I've attempted this in a few cases. I can talk to people about this afterwards. And trying to implement these gauge conditions, they fail pretty spectacularly, in the sense that it doesn't seem like we get far enough into the interior before something goes wrong.
Frans, what do you mean by circular symmetry?
That's with the 2 + 1 dimensional case. So spherical symmetry.
I see. It's 2 + 1 and you've got one circle.
Yeah, so you can think of it as sort of a slice of the equatorial plane. Yeah. Okay. Oh, and then the other thing, which is just an aside also, and I guess Hans is going to be talking about the cosmological cases more. So if there is a space-like piece to it here, and it's sort of this BKL type, the other problem that we can anticipate is it's going to take a tremendous amount of computational resources to resolve it. Because the one issue with numerics, not an issue. Okay, so we get a solution to within some amount of error, and we can estimate that error, and we can guarantee that or not guarantee, that we can give confidence that it's actually close to the continuum solution if we're in the convergent regime. And to be in the convergent regime, we have to resolve features. Everything has to be well resolved. If something is not well resolved, we don't know where we are. We can't place error bars, and what that solution is. It's kind of arguable what it is. And so if we get a lot of structure that forms, we'll need a commensurate amount of resolution, and that could be another showstopper. If we get to a point where sufficiently complicated structures are forming, then we'll just run out of computer resources. And that's probably what's going to happen in the space-like part. And so let me just show you an example of the complexity that can arise in that case. And here for the so-called cosmological singularities, and again, that's kind of a conjecture that this part of the singularity might be similar to these kind of cosmological singularities. So there's no exterior. The whole space-time is just that interior part. And in that case, because there's no exterior, or perhaps that's one way you can think about it, because there's no exterior, the gauge problem is a little bit easier. We don't have to worry about this very disparate time evolution between an interior and exterior. And then it turns out that the study of the approach to the singularity works quite well in constant mean curvature slicing. So this is an example of a simulation with David Garfinkel of, I guess, a Gaudi type model. We have it's toroidal topology, so in X and Y, and we have a symmetry in the Z direction. So this is our entire universe. And now we set up initial data that we are approaching to a big crunch, sort of a cosmological singularity. And in these constant mean curvature slices, so here t = 0 is the start of our simulation, t = infinity is a singularity. And we can normalize things by sort of powers of the overall expansion, or the Hubble the Hubble expansion. So what I'm showing you here is on each t = constant slice, kind of the part of the curvature that you can sort of colloquially associate with shear energy, which then is just going from the Hamiltonian constraint and identifying sort of the shear part of curvature as energy. And here we can normalize it between -6 and 6 after factoring out the overall blow up as it approaches the singularity. So this is actually blowing up, but we're factoring out the overall blow up. But then what's going to happen is you're going to start seeing these Kasner bounces. And what's even more worryful, troublesome resolution-wise, is that sort of certain codimension 1 surfaces here fail to undergo Kasner bounces, and then they form these so-called spikes. And in terms of this time coordinate, these spikes narrow exponentially. So very quickly they become unresolved, and it's usually you think things would crash if they're under-resolved, but it's kind of surprising. But it's probably a fact that here things become local, in the sense that the equations kind of morally become ODEs. We're solving PDEs, but they become ODEs. So the fact that we're getting these unresolved features doesn't cause the simulation to crash. So we can continue evolving with the caveats that we really can't say anything about the actual solution where the structures form. So this is more to illustrate the kind of complexity that could arise in the space-like part if this is what happens in the interior. So there we have kind of the first set of Kasner transitions. There it fails to jump and we get the spike-like feature. Now there's another transition that happens elsewhere. We form other sort of spike-like features. And this just seems to keep on going. So additional Kasner bounces, there things fail to bounce and we form more spikes, etc.
So what do we see? So what is this function? Is this Gaudi a Gaudi space time?
Yeah, this is So this is so in some sense each point is a Kasner-like.
Okay, but what does this depict? So one picture, time equals 45.7. Is that what is it? It's one scalar valued function. These are
So this is the shear shear of the spatial energy density of the slices. So it's a part of the related to the vial. It is related to curvature. It's part of some projection of the vial tension.
okay.
Spatial slices. And so, essentially, so in terms of these normalized values between -6 to 6, so if you had, like, say, a Kasner spacetime, so you pick a point on the Kasner circle, it's going to have some value. And so for a while, it stays on this, close to one of these Kasner circles, but they're unstable. And so at some point, it undergoes a mixed master bounce to another point on the Kasner circle.
Okay, so each color is a particular Kasner?
Right. And so what you can see, so we started with initial data where they were all kind of close to a certain region on the Kasner, and then transitions started to happen.
Okay.
But in some places, the transitions failed to happen. They just kind of stuck there.
Right.
And so you get this mosaic that presumably gets more complicated, and as like we're not that close to the singularity yet, right? It's a T equals infinity.
Now that we know, could we see it again? Because now that we know what we
right. So okay, so yeah, so we kind of all in this room. So now these regions have bounced from there to there. But so along this line, they stop bouncing now, so they keep each point kind of, and it seems to be the case that each point like kind of locally undergoes sort of this mixed master dynamics in a way which is kind of independent of what happens elsewhere. And then they just, it keeps going. And this particular mosaic structure that's forming is just because of the initial data that we picked. The point is, if this kind of structure, if this is sort of developing in this region, as we're approaching that, this structure is going to be developing in this case, and so we're going to have to resolve it. Or probably the more practical situation is if we want to get to the Cauchy horizon, if such a complicated kind of BKL type scenario develops, we'd have to excise it. We'll have to say, okay, it looks like it's developing. Let's cut it out because we can't resolve it.
Have you tried zooming in on the spikes? Can you resolve the spike a little better and see what happens?
Yeah, so the not in this particular case, but so if we then go to one plus one dimensional simulation. So this was with a former postdoc Wei Chet Lim, I guess he's now in New Zealand. So he defined so if we just look at, so just imagine a cut through a spine. Then yeah, he devised this coordinate condition which kind of continuously zoomed in with a spike. And I guess the interesting thing in that case of what happened is, so you want to think that sort of adjacent regions, they undergo Kasner bounces and the spike is left over. But then in some sense, then the adjacent regions undergo a second bounce and then the spike catches up. So eventually the spike does bounce. So at least, I guess perhaps Hans knows better about, but there was, whether all spikes are permanent is unknown, but in this particular case, eventually spikes undergo transitions as well. But then, yeah, that was just looking at the one-dimensional case, and again, trying to follow this exponential decay. That was incredibly challenging in the 1D case. In the 2D case, I don't know how you go about generalizing it.
What's the time coordinate that you gave for the previous video?
Yeah, so each t equals constant is a slice of constant mean curvature, and then we rescale it by there's still, you can rescale it in time by any function of itself, and it's such that t equals infinity is the singularity. So essentially, we define the Hubble parameter. So this is the shear of the flow. So the divergence of the flow, we define it to go like e to the minus t. The constant times e to the minus t, and that's sort of the rescaling.
Are the spikes in this picture invariant with respect to changes of spatial coordinates? Like, is there anything invariant about anything coordinate invariant about this picture? I understand a
So-
foliation, a time foliation has been chosen, but
Okay, the fact that the spikes do form, I would say that that's coordinate invariant. Their exact structure. I think that the fact that they will. Okay, so you can't quite see it here, but they do have a particular profile, and it seems to be that based on the properties of the adjacent Kasner spaces, you can sort of get some analytical approximations to the shape of the spike. That shrinks exponentially, and I think the exponential shrinking will be because of that first of time coordinate. But the shape of the spatial shape is going to be coordinate dependent. You could probably, perhaps, you pick your spike point and you form some orthonormal tetrad. If you tie it to constant mean curvature size, you could probably get some more universal description of the shape. But in this case, it's going to be somewhat tied to the coordinates.
But somehow in the 1+1 dimensional picture, I guess how the set of spikes on you talk about the singular boundary, and the set of spikes is measured 0. Is that true?
Well, I mean, so generically, you only have finitely many.
Finitely many.
Yeah, so for generic, I mean, you can have solutions with infinitely many spikes, right? In Gaudi, let's say, right? So you relation point. So, but that situation is unstable. If you perturb such a solution, you will get finitely many spikes. That's a generic set.
And these should
And it will
be
be low velocity, as it's called often. There are high velocity spikes which can occur, but these are also unstable. There are finitely many low velocity.
in the higher dimensional case. They should be co-dimension 1 objects on the singular boundary, or
Yeah, I mean, what's happened in the oscillatory setting is of course not so clear, right? And so, I mean, so in like Gaudi, there are of course explicit construction. So going back to Alan Rendell and Marcia Weaver, right, like 20+ years ago, right? And there you have, and I mean, the one aspect of the spike in that setting is that you don't see the bounds. I mean, so I mean, the thing is that it goes back to, so the bounds relates to eigenvalues of the expansion normalized Weingart map. I will get into that in the next talk, right? But I mean, so there's a specific relation between the tip of the spike and the base of the spike, and this is related to sort of eigenvalues of the expansion normalized Weingart map of the leaves of the foliations. So that in that sense, I mean, okay, it's foliation dependent, but otherwise, I mean, there are certain, I mean, the relation there's some geometric significance. But the point is that you sort of, if you look at a spike from a causal point of view, you're actually not this violent spatial loss. I mean, if you really pick a point on the singularity, right? I mean, say this is the tip of the spike, and you look at the causal future of that point, you're actually not going to see these violent transitions. So the violent transitions are like, it's like parabola somehow in a causal perspective. So if you go in, so if you really focus in one causal curve going into the singularity, you look at the causal future of that, and in that region, you will not see that violent oscillations. In the Gaudi setting, I don't know about this setting. Sorry.
Very useful, interesting aside. Thanks for all the questions. And thanks for the answers. Okay. Okay, so now, okay, present day tractable solutions. And again, I just want to say a lot of progress has been made in the last couple of decades on the mathematical formal front. And I'm not going to say anything about that. People here have and will say things about that. And the numerical front, again, to deal with these coordinate issues, we have to restrict to spherical or circular symmetry. So unfortunately, then, there are significant compromises that one has to, significant restrictions that come about. So in the 4D case, if you want to have a Cauchy horizon, you need charge. And of course, in 4 dimensions, in spherical symmetry, there's no sort of gravitational wave degrees of freedom. So all the dynamics of the space-time is governed by your matter model. So you can form black holes with Cauchy horizons, but if you want to have that, hopefully that says something about what happens in the vacuum case, where it's sort of gravitational degrees of freedom. It's arguable. You can hope that the matter dynamics driven interior is telling you something about what gravity itself would do. So again, on the numerical front, there have been several works, starting back, with Brady and Smith and Harden Piran, and more recently Kessler, where they've looked at the formation of Rice and Nordstrom black holes in spherical symmetry. I'm not going to go over the results because it's kind of consistent with what people have discussed before and kind of the results that I'll show later, with a few differences. And again, but then the open question, it's not really clear how to sort of interpret that beyond spherical symmetry, and it's more like we hope that it's going to give us sort of more, that the qualitative features are generic in some sense. Okay, so this is now, so now let me sort of talk about gravitational collapse in 2 + 1 dimensional ADS space-time. And this is work that was essentially, 100% of the work was done by my grad student, Alex Pania. So this is essentially all of these work that I'm going to be talking about here. So what we wanted to do was, again, we restricted to these toy models, but if we go away from 4 dimensions, we go to 3-dimensional gravity, there actually is a scenario where we can form Cauchy horizons with angular momentum. And that's with sort of collapsing to asymptotically BTZ black holes. So one way to sort of kind of think of it is, this is kind of like an equatorial slice of the Kerr space-time. So of course, when you 4 dimensions, when you add angular momentum, you're introducing latitudinal dependence, going away from Schwarzschild, but a slice of Kerr is still circularly symmetric. The equatorial plane of Kerr is circularly symmetric. Now, one thing is we can do this without a cosmological constant, because there are no black hole solutions in 2 + 1D or 3D gravity without a cosmological constant. It's kind of remarkable that just sort of adding a cosmological constant, particularly a negative cosmological constant, so that the space-time becomes asymptotically anti-de Sitter, there are black hole solutions. And they have surprisingly many qualitatively similar features to Kerr black holes. These are the so-called BTZ, Donatos, Teitelbaum, and Eddy solutions that were discovered in the early 90s. Okay, so now we've got another toy model. The plus side, perhaps, compared to the Reisner Nordstrom type examples, you've got actual angular momentum that we can use to generate Cauchy horizons. One of the downsides is the same as the Reisner Nordstrom examples, is that in 3D gravity, there's no gravitational waves, there's no propagating degrees of freedom. In fact, the Weyl tensor is identically 0. And so again, matter governs all the dynamics of the space-time in some sense. Then two of the other problems is, unfortunately, 3D gravity is very different from 4D gravity. So, I think that the problem with that's going to be that, well, as you'll see, we get some features that look, what you could imagine is qualitatively very similar to what one might get in 4D. If it turns out that the 4D cases do exhibit some of these features, you can say, okay, that's interesting. Another case where these class of black holes show what's happening in 4D. If the 4D case shows something completely different, no one will be surprised, because 3D gravity is so different from 4D gravity, just not even with black holes. So that's a big caveat with these studies, is it's going to be arguable if there's any connection that we'd be able to make. So perhaps, the takeaway might be, let's just appreciate the results from 3D gravity on their own. And of course, the other difference is that this is now not asymptotically Minkowski anymore, it's asymptotically anti-de Sitter. Whether that's a major difference or not, that's, that is something that we have to live with this model. Okay, so let me just briefly describe BTZ black holes before showing what we got. So this is the metric, and I guess sort of the Schwarzschild-like, Boyer-Lindquist-like coordinates. So basically think of it as an equatorial slice of curve, but the angular parameter that is traditionally used is theta. So this is actually the phi in curve on the equatorial slice, but we're calling it theta. So it's a 2-parameter family of solutions, mass, angular momentum J. And it sort of looks like a black hole-like solution. Now, one thing that's very interesting about these solutions is that they spaces of constant negative curvature. So there's actually no curvature singularity. And in fact, you can form, you can come up with these metrics by just taking pure ADS and making various clever identifications within ADS. So in some sense, you can almost think of these as like topological constructions in pure ADS. So the Penrose diagrams are very similar. The one obvious difference that you'll immediately see, of course, is the infinity of ADS space-time is time-like, it's not null. So that's the one difference. So you've got these flat regions, but other than that, it kind of qualitatively looks the same. So for example, this is the non-rotating Schwarzschild analog. Here's the event horizon, future and past singularities at R equals 0, and this is time-like infinity. And here with the maximal analytic extension of the general solution, the Kerr solution, sub-extremal. So again, there is an extremal limit. So later I'll show results in terms of the A parameter and not this J. So A, you can normalize it to between -1 and 1. So in the A less than 1 case, you've got a similar Penrose diagram with, again, these multiple, this ladder of universes. Say this is our universe, this is our asymptotic infinity. Here's the event horizon, here's the inner horizon, then here's this inner region as well.
Did I understand correct? But even the left picture, there's no singularity. It's ADS space by acting by
Yeah,
something.
it's the same constant curvature as ADS.
R equals 0 is not singular.
It doesn't have a curvature singularity.
It does not have a curvature. I see.
Right, but I'll get on the next slide, I'll tell you, it's actually very pathological. So, right, so, all right, so you said, okay, so there, yeah, that's like, it's got ergo regions, etc. People have shown that there's certain no hair properties, but in particular, like it's a space of constant curvature, but R equals 0 is still pathological. So in the case of the Schwarzschild like solution, it's also tidally crushing. And so you can see that the same properties occur in like what you expect in Schwarzschild. So outside, R equals constant or time-like. Inside, they switch to being space-like. So progression. So once you cross R equals R plus in the Schwarzschild case, you flow in time from R equals R plus to R equals 0. But R is still circular circumference. So it says that any object that crosses into this interior region, any extended object, so think of them as rings as opposed to spheres, they are necessarily crushed to 0 circumference in finite time. So R equals 0 is a crushing singularity, even though it's not a curvature singularity, which is kind of bizarre. And then the same problems happen in the Kerr space-time with this time-like R equals 0 branch that, and so here it actually extended across to -R, but they sort of cut it out there. So sorry, these diagrams are from the BTZ papers, because then there's some similar chronology problems that you have in Kerr, that you get closed time-like curves in that region. So it resembles those features.
And can it be shown that the metric is not continuously extendable beyond the R equals 0 in the J equals 0 case?
That's interesting. Yeah, I don't know if anyone's looked at that.
It's conical. My get
Problem for yeah.
Yeah.
it might be conical. If it might be like a modeled on a cone of not angled not 2 pi. Maybe that's the local behavior. If it's coming from a smooth metric by modding out by symmetry.
Right, yes, that's kind of why it's kind of a cone.
Yeah.
Okay, but I think perhaps one of the most interesting properties is, so like, based on the fact that you can form this by identifications, you might think that these are just, that's as far as the analogy extends. If that were the case, then yeah, it wouldn't be relevant for this problem, but perhaps most interesting here is you can actually form asymptotically BTZ black holes by gravitational collapse. So there've been several examples where people, that's sort of the analog of the Oppenheimer-Schneider. So again, so these are the, the Maxwell diagrams, but as with the asymptotic flat cases, just cut out these parts of the Penrose diagram, start with some regular data and ADS. So people have looked at dust collapse, shell collapse, scalar field collapse, and you then dynamically can form a black hole that asymptotically, so in this region, approaches a BTZ space-time. So the exact solutions are these kind of topological solitons, whatever you want to call them, but you can actually form them dynamically. And then, of course, the interior structure is going to be very, very different from what these constant curvature vacuum solutions basically tell you. Okay, so now I'll sort of show sort of what we found in the few case studies that we looked at. So this is the metric answers that we chose. And I told you like resolving this gauge problem is trivial in spherical and circular symmetry, because this is all that you have to do. You just write the RT sector of the metric to be conformal to Minkowski. So R and T, R plus or minus T are null directions automatically. So evolving it in these coordinates, you basically just immediately get the Penrose diagram. You still have to worry about where, if you run into a singularity, before you've evolved the space-time, you have to excise that. But so that still has to be done. But because it's just two coordinates, it's actually trivial to do. So this is now R bar. Notice that this is not R. So the actual proper circumference is not this coordinate R. So this is the proper circumference that we want to look at. And then just all the relevant metric functions now become functions of R and T. So these are the PDEs that we have to solve. So I say we're going to be looking at scalar field collapse. But the same thing as in 4 dimensions. If you wanted an axisymmetric scalar field can carry angular momentum. Here a circularly symmetric scalar field can carry angular momentum. But then we do the usual trick where we superpose two scalar fields. One, we, for example, give a sine theta profile, the other one a cosine theta profile. And then in the stress tensor, it's going to be sine squared plus cosine squared. And so it's circularly symmetric, but there is net angular momentum. And the easiest way to do that is just with a single complex scalar field. So the stress tensor is real, the space-time is real. This is just a simple trick so we can get angular momentum. And this is kind of the ansatz for the scalar field. So again, this is just we choose the sort of m equals 1, if you will, azimuthal dependence. This is just a factor so that our regularity at the origin is simpler. And then these are the real and imaginary components. And so these are essentially the two scalar fields that we're going to use to, that's going to source to the Einstein equations to drive the dynamics of the space-time. Yeah, well, let me just sort of skip over the numerical methods, except just to mention this thing about singularity excision. So again, we can't get to an actual singularity. Codes don't get there, but they get kind of close in the sense that things start to blow up. And empirically, we found when those two metric functions A and B get very large, then things tend to blow up. And we've, based on convergence studies, etc., we find some threshold value of these functions, and when they cross that threshold, we excise the causal future of that. And so, one thing, I guess, to the question is, with this kind of thing, we can only ever uncover space-like or null singularities, but does a time-like singularity make sense? In the Einstein equations, well, not really, because you can imagine if there is a time-like singularity, what will happen is you'll run into it, things will go infinite, but then you have to excise the causal future, which is a null boundary. So you'll form a Cauchy horizon. The Einstein equations can't tell you what happens across that. So you can interpret. So if the excised future of that point is non-singular, you can say perhaps a time-like singularity form. But in fact, so that's what but in any of all the cases that we've looked at, just a few cases, we never found a situation where the causal future of what we call a space-like piece of the singularity was non-singular. In fact, we didn't actually find interior null parts of the singularity.
But there should be non-generic such thing.
Yeah, there should be. So and actually, so this suggests that this is a situation where it's kind of close to that. But again, we've looked at a small handful of very specific initial conditions. Like the cases that we looked at, we didn't find such situations. But yeah, I think, and yeah, right, so. But that would be something that you would monitor in these cases. So you excise the causal future of what seems like it's approaching a singular point. If the curvature is finite on that, then yeah, it's a Cauchy horizon, but it could be the signaling of a time-like singularity. Okay, so now let me show you the results in terms of the Penrose diagram. So there are a couple of things that I'll want to focus on, and one is what happens with this set of cases as we increase the angular momentum and hence the spin. So the A equals 0 case I'm not showing here. That's one where it's just it's a space-like singularity all the way till the Cauchy horizon. So once we have some spin, we have both sort of a Cauchy horizon piece and a space-like piece. I want to show you what happens as we increase the spin. Let me just sort of explain this, like this plot here. So on the left is the color coding here, sort of on this scale, depicts the proper circumference of this R bar coordinate. So this is a function of our R and T. Just so this is the ones that give us the Penrose diagram, but the R bar is a proper circumference. And this right one is the Ricci scalar. So we start at T equals 0 with some initial clump of energy in the scalar field. We sort of give it roughly an ingoing pulse so that it quickly forms a trapped surface. And so as we evolve here, so at this time we start to find a trapped surface. So this white hatch region shows where there are trapped regions. This R plus and R minus, these dashed lines are, so at this point we can measure the asymptotic mass and spin of this BTZ black hole. And based on that, sort of the vacuum solution, what are the proper circumferences of those BTZ black holes? These are these lines. So this is R plus, this is R minus. So you can see that the outer trapped surface or the apparent horizon sort of very quickly asymptotes to R plus, the actual proper circumference on the black hole. This inner one in this case is not anywhere near what the inner trapped region does, or the inner boundary of the trapped region, and that collapses to R equals 0. So, okay, so yeah, so we form a trapped region, we form this. This is the Ricci scale, so I'll explain a little bit more about it. So again, we can't go to infinities in the code. We can sort of get to some point, and then we can try to extrapolate to where we think things are going to blow up. And that's this dashed red line over there. And if you look closely, it's not coincident with the end of the simulation. And that's because we're extrapolating to where we think the blow up is going to happen. And it appears that there actually is, that the Ricci scalar and the Kretschmann, which is kind of the same here, so they related, is actually diverging on the future boundary of this. And this boundary is actually everywhere space-like. It kind of looks null, but it actually does have a bit of a slope, so it actually is space-like. And this seems to be the Cauchy horizon, which is null. Okay, so again, despite this big kind of a weird shape, this is kind of consistent with that picture of what we expected. So Alice, you're frowning. So.
No.
That's lucky. Okay. So the first thing I want to do is sort of like what happens now as we increase the spin.
So can I just before?
Yeah.
So the different colors, the different, right? There seem to be oscillations in the Kretschmann scalar near the space-like singularity.
Yeah. And they growing in frequency. So I'll show you an example of what the scalar field is doing. And it is oscillating, and the frequency of the oscillation seems to diverge. In this case. It's also by the case here, this actually is R equals 0. It's more obviously close to R equals 0 here, but this also extrapolating, it is going to R equals 0. And then here R is increasing, so R bar, the proper circumference, is increasing from R equals 0 to R plus along that surface. Okay, so now we're going to a much higher spin. A is 0.77, and so there are a couple of qualitatively interesting differences. First is here is actually a region where the inner part of the trapped region actually is pretty close to where you would expect it to be from the BTZ solution. So it actually does kind of follow along with R minus for a while. But then at some point, it kind of collapses down to R equals 0. And so the entire interior, in some sense, becomes trapped. The space-like part of the singularity has now shrunk to a very small part of this, at least coordinate RT diagram. And the other interesting difference, though, if we extrapolate to where we see blow up, we actually don't see, in this case, any blow up along the Cauchy horizon. That little dashed region there of red, that's the only place where we extrapolate where curvature is blowing up. So the interesting thing is, yeah, so we've increased the spin, we've increased the relative size of the Cauchy horizon part toward the space-like part, but here, in fact, the Cauchy horizon has stopped being singular. So this might be a peculiarity of 2 + 1 dimensions, and it's actually consistent with the previous linear analysis of Real, Santos, and Diaz. So they looked at the scalar field propagating on just a fixed BTZ background. They found that with spin, the scalar field, as you approach the Cauchy horizon, has increasing regularity. And so perhaps it's not surprising that then, since it's the scalar field which is really governing the back reaction of the metric, if it's becoming increasingly irregular, then likewise the geometry should be increasingly regular. And it turns out to be, and that the cases where we stopped seeing singularities are pretty close to these boundaries that they find. But then actually even perhaps more interesting, another interesting thing, now if you go to even higher values of the spin, the space-like branch vanishes completely. And so here now the entire space-time doesn't have curvature singularities. There's still a Cauchy horizon. There's no space-like part to it. And here the trapped region also, doesn't quite hang around where we expect it to be, but there's a small trapped region, but it doesn't collapse to R equals 0. I don't know if you can take any conclusions from this for the 40 case, but it's a pretty interesting rich structure here. So I've got 5 minutes left, so enough time just to then. The last thing that I want, before I get to that, let me just show you some examples of how we kind of sort of data that we can use to sort of show the extrapolation. So this is just to show again the behavior of the scalar field on a null. This is for this. What is the left figure is this case. So I'm plotting the scalar field on a line that intersects the Cauchy horizon. In this case, and one in this case, and also, and actually in this case, the Kretschmann scalar as opposed to R, but again, they're the same here. So these two figures are from the low spin case. And so yeah, you can see the oscillations that's happening in essentially the magnitude squared of the scalar field. And correspondingly, the Kretschmann scalar seems to be blowing up. The case where the Cauchy horizon seems to be regular, there's some oscillations, but it seems to asymptote to some value. And the curvature seems to go to some finite value. Similarly, if we look now at the origin, so I showed you examples for this where there was a tiny little piece of the space-like branch and the one where it was gone, but just a couple of other cases as well. So we just look at Ricci at the origin. This is kind of the blow-up cases versus one blow-up case versus 3 that seem to be singular. But essentially, as we increase the spin, it seems to be more and more regular at the origin. And incidentally, how we find that little red dashed surfaces, it's purely by extrapolation. So we say if it looks like it's blowing up, we assume it's some power law blow up to some time TC, and then we try to fit it. We fit these parameters. So there's nothing theory informed about try to find the surface or blow. It's purely a fit to the data, but it's sort of data like this, and we fit along coordinate R equals constant lines, and it's fits like this that gave us those little red dashed lines that I showed on the previous figures. Okay, so the last thing I want to talk about is now another interesting thing that seems to happen in the interior, and this is a so-called Marolf-Ori focusing effect. So this is something that Marolf and Ori asked about 15, 20 years ago. So we know that, and this is an example of the eternal picture again. We know that expect interesting things to happen at the Cauchy horizon because of this blue sheet phenomena, the infinite blue shift, right? So radiation from the exterior that's falling along the Cauchy horizon gets infinitely blue shifted. And so there's some interesting back reaction that happens. And so they asked, well, the inner horizon, from our universe's perspective, this is an inner horizon. And if we like replace this with the collapsing problem, they asked, well, what if a similar structure forms in the case of a collapsing space-time? Now, of course, there's a question like, does such a structure actually even form? But if it does, there might be similar interesting behavior that occurs, because basically these are the same kinds of things, the same kinds of structures in space, time. The differences are, of course, there are quite a lot of differences. Well, the first one is we don't even know if this forms. And actually, if you think back by the diagrams that I showed, it doesn't kind of look like there ever really is an inner trapped region that very closely matches or minus, perhaps for parts of the space-time, but it doesn't quite seem to be the case. But in any case, if it does form, there might be some interesting behavior, but also the radiation that's flowing along this is going to be very different from the late time sort of whatever decay of scalar field that's crossing into the Cauchy horizon. So there are a couple of significant differences, but in any case, they looked at this and they argued that there actually would be kind of drastic effects on the geometry based on this kind of a focusing effect. And as essentially you could just get this from just looking at geodesics on the exact space. And they didn't look at BTZ, they looked at I believe Rise and Nordstrom, but we can do the same with BTZ. So imagine that this is collapsing, this is producing radiation that goes outwards. Now, if this is exact BTZ, which is what we've done here, and what you can ask is, okay, here's sort of some congruence of outgoing null radiation or scalar field energy in this case, with some initial characteristic proper with delta R naught. And now you ask, so now an observer at late times falls and crosses this, how concentrated do they experience that energy to be? And you can actually just from the geodesic equation, you can show that it becomes concentrated by this expression. So this is an advanced time that goes to infinity, approaching the Cauchy horizon. This is the surface gravity of the inner horizon. So it exponentially concentrates. And in fact, if you cross this thing up very close to the Cauchy horizon, you will experience that amount of energy in an ever shorter, will be ever more concentrated. So they argue that there'll be a similar strong back reaction on the geometry, that essentially the whole geometry will be focused. And I forget exactly what kind of calculations they did to sort of justify this, but they said that there'd be drastic consequences. But of course, all this depends on, well, does a similar structure form in the interior? And so again, I showed you things where, okay, here you can say, so perhaps there's something similar is forming, but at late times it's different. And this is the kind of a late time effect. But in the other cases, like it doesn't look at all like that's happening, at least from these diagrams. Here, okay, perhaps. But the kind of the surprising thing is that we do see a very strong focusing effect, regardless of the spin parameter. And that's sort of illustrated here. So now this is the 0.77 case. So let's just go back here. It's this case. And so what we did here is, so now these black lines are contours of constant proper circumference. So this is the outer horizon. This is 3 times the outer horizon. And so you can see, this then wraps around and goes to R equals 0 here and here. And this is the Cauchy horizon, which is again, so R is decreasing along the Cauchy horizon. So that's another significant difference in the back reacting case versus the static case, where this was just a constant, so it's decreasing. But in any case, so what we did is at certain times here, we just dropped a geodesic from rest, a particle from rest, let it fall into the black hole and say, how does it evolve as a function of the proper time that it measures? And these are the curves. So here you can see it's decreasing in proper circumference until it reaches some feature around here where it's very quickly accelerated, and the rest of the journey down to R equals 0 happens very, very quickly in terms of proper time. And the amount of proper time decreases the later the observer is dropped into the black hole. And so in some sense, what seems to be happening, there's a feature that develops in the geometry that when observers fall into it, they're accelerated to such high velocities that the interior is like length contracted into an ever smaller and smaller region. And so here they just fall in with sort of a regular rate, and then suddenly they're accelerated all the way to this point. And of course, what's disastrous about that for observers, this is, the proper circular circumference. So again, if this were an extended object, it would be crushed to zero radius in ever and ever shorter time. So this kind of focusing feature that whatever it is that forms in the geometry here is kind of tidally devastating to these observers.
Frans, these are particular observers. So these are observers in particular that don't cross the vertical horizon.
Yeah. So
So they're in the limit trying to, some sense to.
they're not trying. They just let go and they fall.
Sure, but
So observers that do this,
Yeah.
that's a completely different question.
because, I mean, in some sense, yeah.
Yeah.
I mean, if you think about it, because these observers are constrained to remain in space-time, and it is.
Right.
I understand that these observers, okay, you can characterize them as, they start from rest, at a late advanced time, let's say outside the.
Right. But so this behavior, you don't see in geodesics of BTZ, right? So they'll just fall in. I mean, there'll be some curve and they'll reach R equals 0 in some finite way. But this fact that the later they fall in, more strongly they're accelerated when they cross like this region. And if you look at sort of, see, this was this case. So if you look at like what's happening with the curvature, okay, there doesn't seem to be any feature here that's standing out that would cause that. So
But somehow I think the idea that, because back reaction has already been featured in the model. So somehow the idea that this has anything to do with a further singularity that you see in back reaction, I think this seems misconceived. So I mean, that this is a geometric feature on these spacetimes, that's certainly the case. But
right.
I mean, you already have a fully back reacting model.
Right. Yeah. So yeah, that's also why we were kind of surprised to see it, because in some sense, okay, you look at a scalar field propagating on the space-time, and you look at geodesics, and you argue that it's going to be such a drastic back reaction that it causes this extreme focusing, which means that the actual back reacting geometry is not close to the one you use to calculate this effect. So you should see something different, but why would you see what you calculated on a background, which is completely different from the back reacting case? But then kind of what's surprising though is then if we try to estimate the rate at which this acceleration happens, and we looked at several quantities, so the amount of time that it takes to cross, I think from 0.75 to 0.9. So the amount of time that it takes to cross this region, how the energy density grows, okay, so the change of the proper thing. So at late times, this is a slope that you got from the geodesic calculation, and kind of qualitatively it matches. So somehow it got some qualitative, well, schematically qualitative aspect of it, despite the fact that in this region, the geometries are completely different. It shouldn't really know what's going on there, but somehow it did. But okay, I guess the more important takeaway, as you said, is this should be your little survival guide. Like, how do you survive if you fall into a black hole? If this doesn't have any bearing on a 4-dimensional black hole, like you might have heard that if you accidentally fall into Sagittarius A star, just relax, don't do anything. Because any acceleration will kind of length contract you towards the singularity, and you get there faster. So you just want to just be on a geodesic without any acceleration. But of course, that's assuming a Schwarzschild case. If it's curved and there's a Cauchy horizon, what this is saying is you better panic and start to accelerate and get to this region as quickly as possible. Like, yeah, it's not just getting to there that's the problem. Like, once you've crossed this region, you're going to get crushed. So that's the important takeaway. Okay, and thank you. So this is my conclusion. Yeah, so I don't know. I'm not going to not say anything. I don't know what this will say about the 4-dimensional case. I think one thing that all these results are starting to show is that the fact that the Cauchy horizon seems to be less singular, or in this case, even non-singular with the high spin cases, might say it could be difficult for quantum gravity, or at least the usual way in which I think that quantum gravity knows how to fix these problems is that it's going to be told that general relativity is breaking down. And the way that we think it's told is that curvatures start to blow up. The radius of curvature drops below the Planck length or something like that. So if that doesn't happen, it's going to have to probably be a very different kind of quantum gravity theory that might resolve the problem if it doesn't do that. On the other hand, it might be that, if Hawking radiation might come to the rescue in the sense that Hawking radiation might allow, it's going to evaporate the black hole, and we might only ever get to that regime where they're in conflict when the black hole is microscopic. And so the entire thing is quantum, but you can speculate on what's the more interesting next steps. I mean, I think the 3D problem is interesting, but probably given how complicated it would be, even in this 3D problem to relax circular symmetry, we might as well just try and go for the 4D problem. Thank you.